appreciate NRGene for giving me the opportunity to speak today. And I would like to tell you are a couple of stories about how the strategy behind Genome Magic has helped us in a couple of use cases, and the value of that strategy we see going forward. But first, just to put in a little bit of context, one thing that we saw when we started working with NRGene some time ago, working with the de novo Magic platform first, but then expanding that into the Genome Magic platform, is that it really represented a bit of a change, not only in capability, but in how you can think about doing experiments or studies going into the future. You can envision a current state where, as we all know, a single reference genome is great to have, and it's certainly a step change over a decade ago or even 5 years ago, but it's still not great. You know, we have reference biases, there are constraints, we don't really have analytical access to all the functional diversity one might want for any given study. And that leads to downstream extra costs, extra time around decision making and applications. And in the end, it's really not leveraging the full power of genomics-assisted breeding, of what we could be doing for the crops. And so in working with NRGene, there's really here the opportunity to test what is the value of taking that next step away from a single reference genome and moving to a spot where you not only have more than one genome, but it's analyzed in context and you have a comparative pangenome to work with. And what I'd like to present is a couple of areas of value that we saw in taking this approach. One of them is more academically oriented, so a smaller use case to show the value in asking questions of a more academic nature where the study is a little more discrete in size. The next use case is a little larger. It's about how we saw some value looking at this tool more on the scale of a breeding process, and where we saw some value on that point. But just to help set the stage a little bit, a lot of the way we see the management of genomes is a migration from single reference genomes to, well, I have more than one genome, but I'm still managing them as distinct entities, to this next step that's represented in Genome Magic, where you're managing all of these genomes as a unit, as a comparative pangenome that you can interrogate essentially all the genomes simultaneously in context of each other. And so first story is about a collaboration that we've been running with David Balcom at the University of Cambridge, working with Kanu Patel and Sebastian Muller on a very interesting study around hybrids in tomato, looking at some of the heterotic components, mainly about transgressive molecular features. And at the start, you can see it's a very common design where we have a common parent. This is a Haberkides line. Two lycopersicin, where you've got their hybrid, and they have differential heterosis. And so the question was, can you do molecular dissection in NGS space and learn anything about how important or not transgressive features are? And one thing we wanted to do that was slightly different from a lot of the work in the literature was we actually wanted to go after the parental genomes before doing the studies, because I think we're all aware of the difficulty in doing epigenetic analysis through proxy reference genomes, and we kind of wanted to minimize that potential problem. So we worked with NRGene to get the parental genomes, the Haberkides and the two lycopersicins, and in comparison, here's the Heinz 2.4 public reference genome, and we're really happy with the results using the de novo Magic 2 software to get ourselves a really high quality de novo assembly that we can work forward with. And so the question then becomes, now what? Most of the literature out there really looks at a hybrid as if it were one thing, not the two genomes that are brought together. And there's really no gold standard for how you analyze a hybrid genome in NGS space yet, but the common ways are to take all of your parental genomes and data from your hybrid and analyze through a proxy genome, which is usually the public reference genome. And that's fine, that gets you to a certain point. Another way of looking at that is to do a SNP-injected approach, and that's also common in literature, where you do some GBS skimming of your lines and then you inject those variants into your proxy genome and do your analysis that way. And that may get you a little bit more improvement, but it's still an estimation, and you get, if you're doing a transcript, you can get a reasonable approximation of the expression and maybe some estimation of parental contribution if you design your study right. And we found that when we had the parental genomes, we had to change our thinking or approach for how we wanted to analyze a hybrid when you actually had the parental genomes in hand. And one is that we had this really nice opportunity to get a comparative pangenome out of this. Even though it's 3 lines, there is still value in getting a comparative pangenome. And so we spot checked this on a few loci, and I'll show you the value of that here in a few slides, but the whole genome study is still in progress. But ideally, you can get each and every feature in each of these genomes compared to each other, where you get chromosomal coordinates as well as some assessment of what the structural differences are between the genomes, and that really aids the interpretation downstream. And at the same time, we started looking at, well, how do we analyze this in NGS space? And we went through a few iterations, and what Sebastian came up with was this idea is we can do this merged genome approach where we actually analyze all the data against both genomes simultaneously. So instead of now estimating expression of a feature and parental contribution, we can get an absolute value of that gene expression and parental contribution. So we tested it, and it's a little more computationally rigorous than the old approaches, but it seemed to have higher rigor, which is great. And here's an example of what that begins to look like. On the left, we benchmarked the SNP-injected approach. And remember, at this point where we're doing this work, there's really no gold standard out there for us to work with. And using our ChIP-seq data, we were able to show that if we were just going through a reference genome, Heinz, or if we did a SNP-injected approach using Heinz, we could see a little increase in value in the Haber-Keides line, which is the more distant line compared to the public reference genome. And so that was great. And we can conclude that SNP injection outperforms your standard reference genome approach. But then we looked at the merged genome approach, and we were looking at our BS-seq, our methylation data at this point. And to explain how this graph works, we have our SNP injected, we have the lycopersicin line, which is injected with the Haber-Keides variants. And you have our merged genome, where you simultaneously analyze against both genomes at once. The top graph is the total number of reads, so these are identical. Here we have parent 1, the hybrid Haber-Keides, hybrid parent 2. And what you can see are some drastic differences in performance based on the approach. So if we look at the mapping efficiency, there's a significant drop in the Haber-Keides and mapping efficiencies. And there's a less significant, but there is a drop in the hybrid genome. And what you wouldn't necessarily know had you gone against a reference genome or just looked at the SNP-injected approach is that this drop is biased against the more distant genome. So you're not necessarily accurately measuring your parental contribution from the genome that's more distant from the proxy reference genome that you're using. And so right away we're seeing efficiency gains, and we're also seeing an interesting decrease in false positive rates. So even though we're looking at the L2 genome, the L1 has a certain efficiency which, when you go against its own genome, drops. And so we're thinking that's some false positives that we're now avoiding downstream from future analyses. And when you look at the total Cs analyzed, so independent, or as a consequence of the mapping efficiencies, you can see that there's a significant difference in the Cs that are available for analysis when you're doing your methylation study. And again, when you look at the hybrid, there's a drop, not as much, but that drop again is preferentially against the contribution from one of the two parent genomes in the hybrid. So right away we conclude, this is just one example, we did other benchmarks, we concluded that having the right genomes clearly mattered and that this merged genome strategy to analyze hybrids offered clear advantages over some of the traditional ways of analyzing hybrids. And so when you look at the consequences, here's the L2 genome, here's the H1 genome, and if you look at the data from the L2 parent, the H1 parent, and the hybrid, we have RNA-seq, small RNA, ChIP-seq, and methylation BS-seq. And when you map them simultaneously, there's a high specificity for the L2 data to map to the L2 genome, very little, if any, mapping to the H1 genome. Every now and then there's a spike, and you can mask that for downstream analysis. Same thing for the H data matching to the H genome. And then, of course, when you look at the hybrid, you get a very smooth mapping across both genomes. And each of these is a very accurate assessment of the parental contribution to the total expression going on in the hybrid. And so what we see is that there's really no universal change in small RNA size, and there's no universal change in methylation state. And anyone who's up to speed on some of the hybrid or heterosis literature will understand that there's some active debate about whether or not hybrids have increased methylation state relative to parents and decreased small RNA counts relative to the parents. We see examples of transgressive behavior across all data types, and it gives us some really interesting ways of looking at the traditional explanations of heterosis, mid-parent, overdominance, transgressive, so on and so forth. So an example of how that really helps is to go back to that comparative pangenome. So normally in a hybrid, you would assume that the proxy genome has the gene, and maybe your hybrid didn't, or maybe it was translocated, and that would just be part of the risk as you do your analyses. And maybe you could do some orthology searching, but you really don't have the physical proximity. And so what this does, having a comparative pangenome, really enabled us to look at the physical location and be sure that that gene in Habrochytes was the same gene in Lycopersicon, and make some conclusions based on that. So as an example here, we have a small RNA allele, and we have two independent loci, just to exemplify. And these small RNA alleles are separated by 2 or 3 SNPs each, and that might be hard to prove that's the same small RNA allele unless you had the comparative mapping showing that that is the right region that you're looking at and that those are the same genes. And when you look at parent H, there is no small RNA expression, and here we have blue is unique mapped and purple is multi-mapped, and these are in quadruplicate. We have methylation data down below. There's nothing expressed here. The L2 parent has some small RNA and some methylation, and on this loci it's the opposite. You have some expression here from the H parent, nothing in the L parent. And when you look at the hybrid, you can see that the hybrid state gains small RNA and methylation at the H1, or in the hybrid for the H1 parent, and disappears in the hybrid for this particular loci. So it's examples of transchromosomal methylation and transchromosomal demethylation, which have been hard to show in the past when you're looking at proxy genomes and may not have had a comparative map to know that these loci are the same. We're not missing this section of the genome in our genome assembly. We're not missing it because there's a PAV or a translocation in our lines compared to the reference genome. We have a very accurate assessment of exactly what's going on in this loci and can make some very interesting interpretations genome-wide about how the genomes are performing in a hybrid context. So a lot of interesting study that we're doing with the Balcom lab here, and we'll continue to work, and hopefully you'll see more from David himself when they're able to present. But the next story to move on to is more on a breeding scale, process scale. And in this case, it's Maize. We want to ask the question, what happens if we can get away from the B73 dependence or dependence on multiple genomes, but treating them as distinct entities, and looked at genome prediction and where that can go and where that can be improved. And I'm sure everyone's seen a number of talks already that explains what genome prediction is, so I won't belabor the point, but basically you've got training populations and you use both genotype and phenotype to predict phenotype on a population for which you have genotype. And there's a lot of constraints if you're working through a reference genome and if you're interpreting population level data through the lens of a specific reference genome. There's ascertainment bias and other problems that creep into your analyses. And so what we were able to do working with NRGene is to ask, okay, we've got 32 genomes worth of Maize haplotype diversity constructed in a comparative map. 6 of these are at the higher 180x genome level. The rest of them are at the 30x genome level. And they're all defining our universe of haplotype diversity. And they're all constructed in a comparative map so that we can actually access the diversity and work through it. And in context, we followed the strategy of using this level of information to project these genome-wide haplotypes onto lines that have a low skim sequencing approach behind them to better understand what's going on in these lines. And so we have about 347 lines from a dihaploid biparental population, and we're testing 2 different reduced genome GBS methods, and we're testing the NRGene optimized skim GBS method that's been optimized for the particular strategy. And we're asking, do we see value, and where do we see value? And right away, we're able to look at the actual genetic diversity that we're capturing, and we can find that using the genome magic strategy, using these 32 genomes in context as a pangenome, we get a significant reduction in false positive SNP calls. We get a significant enhancement to imputation accuracy, and that's only measuring the enhancements based on the GBS methodologies. We really haven't benchmarked the enhancements yet due to their haplotyping strategy, and that'll be coming soon. So at least a 4x improvement in imputation, significant drop in reduction of false positive SNP calls. But most importantly to our corn community and to our breeders, we finally had analytical access to that 75% of the diversity that was not a SNP. So not only could you find structure, but you now had access to structural variants for downstream analyses. And within the context of our particular genome collection, of the total variation we had access to, 25% of it was SNP-based, 75% of it was non-SNP-based. And we also had access to that 10 to 50% of any given genome that was not in a reference genome, like such as B73. So these lines were diverse enough that their alignment with B73 kind of tailed off the further away from B73 you would get, as you'd expect by genetic distance. But now we had access to that information in a way we can use it. So more diversity outside the reference genome, more accurate genetic data set, more types of diversity that we can use for our analyses. And when you look at the GBS approaches, if you look at some of the standard restriction enzyme, reduced genome, or amplicon-based reduced genome approaches, and contrast that to the NRGene skim approach, which is a whole genome shotgun skim type of approach, looking at only the 25% of the variation that's a SNP to get an apples-to-apples comparison with the other methods, we're seeing about a twofold increase in the number of haplotypes we're resolving across the genome. We're seeing a twofold increase in the resolution of the data points that we're analyzing on these GBS lines. And we're seeing significantly reduced missing data rates across the board based on these populations. So in a very large sense, you're getting a lot more bang for your buck, more diversity, more resolution, more haplotypes, less missing data, stronger imputation, less false positives. It was a much cleaner, more robust data set than we've been able to use before in a genome prediction sense. And so when you look at how this actually impacts the ability to do genome prediction, we were surprised by the value we saw, truthfully, because this is a dihaploid biparental population, not a lot of recombination in the population, very easy to predict using standard genome prediction models using conventional SNP-based, chip-based, TACMAN-based means. Even that aside, though, looking at trait 1, we're able to show that GBS methods outperform chip-based methods extensively, not necessarily in raising the peak predictive power of the model, but in how soon you can reach that. So basically, we can reach peak predictive power with 10 to 20-fold less markers used, and that directly speaks to the cost of doing these kind of genome predictions on the scale of a breeding pipeline. And we can also show a convergence that the GBS methods, which are more of an open genotyping method rather than chip-based methods, which are a closed genotyping method, they converge very, very quickly. This is a density-dependent analysis all the way down to, I believe, 10 markers, all the way up to, I believe, a few thousand markers. And you can see rapid convergence of the models using GBS methods and a lack of convergence until much later using the chip-based method. So that's great. You can get actually through historic GBS data sets, you can actually get new value by putting them through the genome magic strategy rather than a reference-dependent pipeline that they may have been put through before. So old data gets new value with this kind of strategy. But when we look at a different trait and we ask, can the skim GBS method optimized by NRGene to work with their pangenomic system, what kind of value that can add? And in this case, we have a trait that's a little bit harder to predict. The CVs are a little higher on the phenotyping, the heritability is a little lower, and traditionally that makes prediction models a little more difficult to work through. But using the traditional GBS, we still see the same convergence, but using the NRGene optimized GBS, the skim approach, we can see an increase in the power of the predictive model. We can get a 10 to 20% increase based on the GBS method in conjunction with their pangenomic strategy. And again, at the lower end of the marker range, there's a lack of convergence of the 3K chip. And again, some lack of convergence using the GBS because this is a more difficult trait to study, and it was also a slightly smaller study. But at the end of the day, we do see a significant increase in the ability to do your genome prediction models. You can raise the ceiling of the model. This model is not quite saturated, and so you can get some enhanced power out of that. And based on this study, you can also get that power potentially with significantly less markers feeding into the study. And so from a breeding perspective, these were really exciting results. We potentially can reduce costs and potentially increase genetic gain by using these kinds of methodologies, a pangenomic approach and a GBS method that's optimized for that pangenomic approach. So in the end, though, a pangenome really is a data management strategy, and the value, yes, in how you put it together, that matters, but more important is how do you get the data out of it. a lot of very interesting papers, some theoretical, some more practical, on how to do pangenomes. Very few of them actually address that downstream need to pull the data out of a pangenome in a way that actually works for people. And what we were really pleased with, though, is that we have all this complex information, 32 genomes as a pangenome represented as haplotypes, 307 lines each through 3 different GBS methods. It's about 10 terabytes of sequence information readily available for us to analyze in real time. And the output was very conducive to existing downstream analyses. They found a way to put this kind of information into a VCF-like report that closely resembles a genotypic matrix. And it took our guys maybe a day to figure out how to tweak this to get it into their existing pipelines. So there wasn't a lot of disruption in how to pull data that we hadn't quite seen before into the pipelines that were already existing. So moving from a reference-based SNP-dependent approach to a pangenomic haplotype-based approach wasn't nearly as disruptive as we thought it would be. These reports were intuitive and easily flowed into the pipelines we were looking at. So to conclude, again, pangenome is really a fancy word of saying data management strategy, and the strategy that NRGene's developed around how to put together these genomes as a comparative pangenome represented as haplotypes did seem to give us a lot of value for where we've looked at it. The fit-for-purpose genomes managed as a pangenome really improved our ability to molecularly dissect hybrids. We expect that the data will be analyzed far more accurately at a resolution and some insights that we haven't been able to maybe achieve before in looking at heterosis. And when we look at a breeding, access to all of these multiple reference genomes as a GBS method really did improve our ability to optimize a GBS method that in turn optimized genome prediction strategies, both in marker number and in predictive power. So with that, I'd like to thank everyone involved, in particular our collaborators at the University of Cambridge, David Balcom, Canyu, and Sebastian, as well as Guy, Gil, Omar, and Kobe, who we've been working with for a couple of years now, and of course our team within Syngenta that's been contributing to both projects.